Right. Good afternoon, everyone, and very pleased to be hosting this webinar for the Supergen ORE Hub. My name is Byron Byrne. I'm a Professor of Engineering Science and hold the Ørsted Royal Academy of Engineering Research Chair in Advanced Geotechnical Design at the University of Oxford. I'm also a co-director of the Supergen ORE Hub, leading on activities for early career researchers. My research focuses on geotechnical engineering for offshore wind and other renewable energy structures, and I've been principal investigator for several major industry projects aimed at delivering new design methods for large diameter offshore wind turbine monopiles, much of which is now routinely applied in practice. And that's the subject of this afternoon's webinar. I'm joined by my co-presenter, Mr. Avi Shonberg, who is a Chief Geotechnical Engineer at Ørsted in London, UK. He has more than 15 years' experience as a geotechnical engineer. Avi has had a focus on offshore foundation design since joining Ørsted in 2014, with a particular focus on suction bucket design, pile load testing, soil structure interaction, cyclic effects on soils, and 3D finite element modelling. He is actively involved in current state-of-the-art geotechnical research and currently a TP member of ISO TC 67 SC7 Working Group 10, TP3 Shallow and Intermediate Foundations. And he currently sits on the SUT OSIG committee. So we'll be giving a joint presentation. Avi will start off with a motivation and industry perspective, and then I'll give an overview of recent research and direction of travel. Before I get into that, I would just like to also raise the opportunity of attending the Supergen ORE Hub masterclasses. There are two that are coming up. There's one on environmental contours and extreme value analysis, but the registration closes very shortly. This will be in Exeter in a couple of days. And then there's a second one which focuses on offshore geotechnics, covering a range of material for people that need to become more familiar with the area. This will be held at the University of Southampton towards the end of May. So if you're interested in either of those, please get in touch. There's the QR code on the right. You can register and please attend. So I will stop presenting now and pass to my colleague Avi, who will give the first part of this webinar.
Great. Excellent. Good afternoon, everyone. Thanks for the introduction, Byron. As Byron said, my name is Avi Shonberg. I'm here in London in the UK. And in part one of this webinar, we're going to discuss why PICASO. What are the challenges, what's been done in the past, and what do we need to do going forward? And really what we're talking about today is the foundation design for offshore wind turbines, which you can see an example here on the right of the screen. And we'll come back to this slide a few times throughout the presentation. But really, what are the challenges? What has been done in the past? And then what do we need to do going forward? So today we focus on monopile foundations. And in general, monopiles are a simple and scalable foundation solution for supporting offshore wind turbines. As you can see here, it looks very simple. They are easy to install, and they're relatively simple for transport and installation purposes. Monopiles aren't the only option available for supporting wind turbines for offshore wind farms. On the left here, we see a monopile, but we also have some other options. Here are just three of the common ones. We also have the suction bucket jacket and the pile jacket, but 76 of all foundations are actually monopile foundations. So we see that it was a trend and still is a trend that monopiles are the preferred foundation solution for many of the wind farms we see being constructed around the world. So what do they look like? They look like this these days. Very long, very large. And as I mentioned before, they're relatively easy locator tubes, but relatively big and easy to move around. And we install them using a large hammer. So very simple. You lift these piles up put them down to the seabed and hammer them in. So just going back just a few years, we have monopiles at Hornsey 2 here, and we could go back even further and further, but just going back just 4 years ago, we have the Hornsey 2 monopiles. And just to give a scale of what a monopile these days looks like, they're roughly 75 meters long 4 years ago and 9.5 meters in diameter. And the Hornsey 2 monopiles roughly weighed around 1,250 tons. And obviously every monopile is different across a site. So we have different water depths across site, different ground conditions, and the monopiles are typically designed to accommodate the site-specific circumstances. So that it does range within a project, but these are some typical numbers from a few years ago. Moving on to today, though, what do we see? And this was just in the news from renews.biz just a few days ago, 5th of May. And Steelwind was celebrating production of the largest and heaviest monopile that they had ever made. And it had a length of around 115 meters and a monopile, a mass of 2,200 tons. So the monopiles, even just in the space of 4 years, have increased significantly, not only in length, but also in mass. And the reason this is important is because this also gives us opportunity for better engineering to better optimize these monopiles as we go forward. So we see the ability to save steel and make these monopiles as efficient as possible as a key target going forward. So in order to do that, what are some of the challenges we need to face? The first one, increasing turbine size. You can kind of see it here in this graphic, but we'll go into a little more detail now. And over time, we've seen the turbine size in terms of the number of megawatts each turbine can produce increase significantly. So from 1991, we started with a 0.5 megawatt turbine. Through the mid-2010s, we got up to 6 to 8 megawatts. The 3.6 megawatt, I should mention, was the workhorse of the offshore wind industry up until about 2010, and then these numbers started increasing significantly. When I plot these numbers up on a graph of time versus rotor diameter, so rotor diameter is somehow linked to, or is linked to the power that each turbine can put out, you can see a fairly linear trend, or potentially even an exponential trend, but it is increasing year on year. And what does this mean? Rotor diameter increasing means bigger loads on our turbines. So the bigger the rotor diameter, the more force is going into these turbines, and therefore into our foundation. So we see turbine size increasing. So what does this look like? A few years ago, this was a 12 megawatt turbine, and here's the Haliade, the GE Haliade X 12 megawatt put up against some other structures, well-known structures from around the world. You can see the Eiffel Tower dwarfs the London Eye, these new turbines. And this was already a few years ago. At the time, we thought these were massive. But now last year already, we can see again from the news, the first Siemens Gamesa 14.7 megawatt turbine was put up at Moray West offshore wind farm. And here's a photo of it actually in all its glory, thanks to ocean winds. And they're really, really large structures these days. So 222 meter rotor diameter. So we're getting much bigger turbines, which means much bigger loads because the wind that these turbines are catching is increasing. And the second challenge we see with time is increasing water depth. As you can see here in the graphic, the earlier wind farms were closer to shore, the easier sites. It was much easier to construct close to shore. And now, as we're going on in time, we're moving further and further away from shore. So just a snapshot back from not that long ago in 2019 from the German wind farm projects, but you can see both water depth and shore distance were increasing with time. So water depth on the right-hand side in green, shore distance to shore on the left. And these days, so in 2019, we saw that the average offshore wind farm depth under construction was 34 meters. And last year, that was up to 38 meters. So if you think about where that plots on this plot that I show above, we're now moving significantly up in terms of the water depths that we are designing these offshore wind farms in. Just to get that point across even more, only a couple of years ago, we had the world's deepest offshore wind turbine installed off the Scottish coast, and that was in 58 meters of water depth. You'll notice that that's a jacket structure, and that's typically because the deeper water sites typically will need to use jackets. But monopiles have been slowly but surely marching onwards to those deeper water sites as well. And what does that mean? So these monopiles, as I mentioned, they're just big steel tubes. When you break it down and simplify them, they're very dynamic structures. You can imagine, whilst they look massive and they look very stiff, when you put a giant wind turbine on top, these things can really move around with the different loads that the environment can apply. So the deeper water leads to a longer lever arm, and that means that we get a lower natural frequency. The longer the lever arm, the slower this moves back and forward at its natural frequency. But we need to keep those natural frequencies above certain limits. So normally what we do is we increase the stiffness of the monopile. And we can do that two ways. One is increasing the steel wall thickness, or the other one is increasing the monopile diameter. Increasing the monopile diameter tends to be more efficient in terms of steel use. So that's the path people have typically taken. So now we're seeing monopiles of 10-meter diameter, 12-meter diameter, and maybe even higher or larger diameters going forward in the future. So both of those things, increasing turbine size and increasing water depth, lead to larger loads and larger demands on our foundations. So how does this really look like in the real world? Well, during storms, and this is from the BBC, and this is a floating structure here. This isn't fixed down, which is why it's moving. But here we are in the middle of a storm off the coast of Scotland in the North Sea. And what you'll notice here is that the waves, not only are they absolutely massive, they're very repetitive, which means these loads keep coming. They keep coming and they keep coming. So during a storm, the waves build and build and build, and they apply repetitive or cyclic loads onto our structure. So during a storm, there can be thousands, if not hundreds of thousands of cycles. These waves are relentless in terms of how they apply to the structure. The structure doesn't get a choice. It sees the storm, how it comes. So these cyclic loads are something we need to deal with from the environment in the water. But then we also put wind turbines on top of our structures that we built for offshore wind turbines. And they have a bit of a different response, but also it leads to these significant cyclic loads. So here we have an emergency shutdown where we've turned off the turbine. So it's got a lot of load on it. And then when we turn it off, it goes back and forward, leading to some significant cyclic loads. And there's lots of other cyclic loads, wind gusts or any vortices around the blades, and we see lots of different cyclic loads. So we can see maybe even up to millions of load cycles over the lifetime of one of our wind turbines. So that's a bit of an introduction about where we're coming from and what cyclic loads are. So now let's look into what's been done in the past. And this all started out, that a lot of the design methodologies started from the oil and gas industry, as you can see here on the left, using what was called the API standards, the American Petroleum Institute. So the original designers for the offshore wind farms took those standards that existed for offshore design and said, let's use that to design these very simple monopiles. So us engineers, being engineers, we simplified the whole thing down to what you can see here on the left, with some springs holding this monopile in place, representing the soil response. And we could calculate the response of the monopile based on some simple formulas, which you can see on the right. So when we push the monopile, as you can see here, we get this curve of force versus displacement. The more you push it, the more it starts rotating over. So we had some simple formulas to apply to these monopiles. There was a bit of a problem, though, when we actually then went and looked at measurements from these monopiles. So on the left, you can see here a system model. So we put our system model together. We put in these API PY curves, as they're called, and we tried to make some designs for these wind farms. And what you can see here on the right is on the y-axis a measure of the stiffness prediction, and on the x-axis we can see the mean wind speed. And what you can see is that all these dots lie somewhere between 5 and 8%, which means we were underestimating the frequency by about 5 to 8%. So something wasn't quite right in our predictions of how these monopiles were going to respond in terms of the stiffness and the frequency. So the PICASO project, which Byron will talk more in detail about later, was launched to try and actually understand the real fundamentals of how were these new monopiles, these much bigger monopiles, responding. The oil and gas piles that these methods were made for were skinny, long piles, and as you could see before, we're now installing very chunky, low L/D, so very stocky monopiles. So that's a large diameter and much shorter embedment into the ground. So the PICASO project, which you can see here, many of the partners, it was consultants, industry, developers, and also a great partnership with academia, went to explore the fundamentals of how these monopiles respond to a monotonic load, just so we could understand the basics. And the result of that was moving from some formulas you can see on the left to a process, which you can see on the right, which included the most modern 3D FEA that we have available to us today. We simplified it down into some one-dimensional FEA, so that's finite element analyses, and then we turned that into site-specific design springs. But we went from some formulas to a process. And this really moved us on in leaps and bounds about understanding what was happening, therefore allowing us to optimize these monopiles even more. However, there was a little bit of an interesting leftover from these API PY curves. And that's that if you look at here, right in the front of the formula, there's this A factor, this factor to account for cyclic or static loading conditions. So if it was cyclic loading conditions, we had a factor of 0.9, so put on our response, which meant we weakened our response effectively. Now, this meant a reduction in the capacity, but also had a significant effect on how we designed the monopiles. And so what we did was we actually applied a static load and then had some cyclic PY curves to account for this loading, this cyclic loading that was happening. Moving on to today, so API standards we used back in the start of the offshore wind turbine industry for the foundation design. But now today, there is no industry standard for calculating this cyclically degraded response, this cyclic degradation factor. Everyone does it a little bit differently. In fact, Ørsted hosted a seminar in September last year at our office in Copenhagen, where we had lots of people come to present about the different ways that consultants and developers and academia are looking into how to calculate this cyclic degradation response. But the summary is that there is no industry standard and everyone does it a little differently. And since this is punishing our monopile design in terms of we have to degrade our monopile capacity to account for this, this is definitely an area we would like to look into. So what does that mean going forward? What we need going forward is a better way to model these cyclic loads and maybe even come up with an industry standard sometime in the future. So what we have today is a static load with some cyclic PY curves where we apply just some simple factors. They do end up getting very complicated in how different people apply them, but in the end, it is what you see on the left, to maybe something in the future where we can actually model each wave coming onto the structure, onto our monopile structure, wave by wave, cycle by cycle, to see its effects. Not only do we need to consider the effects on the monopile capacity, but also the accumulator rotation. So how will this monopile look after its full design life? And as a result of that, PICASO was born. And I appreciate until now you have no idea what PICASO even was. But PICASO stands for Pile Cyclic Analysis, Oxford and Ørsted. And on that note, I'll hand back to Byron to continue on with the presentation and give you a bit more detail about what we've been doing for the last few years.
Thank you very much, Avi. I'll just get my part of the presentation going. So, yes, I'm delighted now to pick up the story to show where we've got to. And I just also say that if you have questions, please put them into the chat. We will have time at the end to go through them. And we'll also have the opportunity for people to ask questions as well. So as Avi has mentioned, the monotonic design problem, in the end, I guess it's a fairly straightforward one. You apply a load to the top of the pile at some distance E above the ground, and you want to try to determine what is the load at ultimate capacity and what is the stiffness at small displacement. And we're going to see a few plots of load versus displacement, with load on the vertical axis and displacement on the horizontal axis. And a typical monotonic curve has a fairly stiff initial section, and then gradually plastically deforms, and you get maybe an ultimate capacity of some form. So we want to predict this, and the PISA project, the central aim of the PISA project was to develop a process to allow a much more site-specific approach to predicting these monotonic load displacement curves. There were a number of different elements carried out by various partners of the academic work group that were involved with the project, but also supported by a wide range of industry consultants and partners as well as the developers. So we had a focus on advanced numerical modeling, a focus on field testing to provide the evidence of behavior. And the field testing is very important. We wanted to have information to allow us to validate new methods, new approaches. The FE modeling, the advanced numerical modeling, was critical for this because it allowed us to design the field tests. Often when you're designing structures, you design them not to fail. But in this particular instance, we were designing the field tests so that we could actually fail the piles. And so it's very important to have accurate calculations to allow us to properly specify, for example, the loading systems and design the actuation systems and so on. The numerical modeling was also very important as it allowed us to carry out calculations for full-scale piles and use those to inform a much more simplified engineering design model, such as the one shown on the bottom left, the so-called PICASO design model, which incorporates not just the PY elements, but also other soil reaction curves. And then we had a stream of work in which we could apply this approach to reasonable engineering problems that the developers were interested in. And actually what you can see in this plot on the bottom right is that the new models predict stiffness and capacity that's much increased on the older models. And the field tests then were used to demonstrate that these new advanced models were more accurate. They could be validated against the testing. Now, all of this work is published open access, and if you're interested in it, you can download all the papers from Geotechnique at the link shown. Here is some evidence from the very large-scale pile tests, the 2-meter diameter pile tests. These ones are at Dunkirk in northern France, a dense sand site. And in this instance, the two piles are pulled against each other so that we can apply the load using a system of actuators that work in concert so that we can apply load and displacement controlled motions to the piles. On the left-hand side, you can see the responses at the two different test sites at Cowden and also at Dunkirk, Cowden being a stiff clay site and Dunkirk being a dense sand site. And then in blue, these are the finite element calculations that were computed prior to the field testing. So they were computed in advance, and you can see there's a very good match between the computation and what we achieved in the field. So this gave really great confidence that well-calibrated and well-performed finite element calculations could predict field behavior. And with that confidence, you can develop your more simplified models on the basis of results from the advanced numerical modeling. So that is the PICASO project, and now this process is widely used across the industry to design offshore wind turbine monopiles. However, as Avi has pointed out, the real loading is cyclic. Here is some example evidence of the cyclic loads that you get offshore. This is from the Draupner platform in the North Sea. This was monitored. And in 1995, it experienced its 1 in 100 year wave event. So the plot on the bottom shows the sea surface elevation with time. And you can see there's quite a lot of very large waves. And in fact, trough to peak, we're talking about 25-meter high wave. So these translate into very significant loadings on the structure. And that's the type of loads that we need to design our structures for if they are to survive their 25 or 30-year lifetime. So capturing cyclic loading, very important. This was the stimulus for the PICASO project, which started in 2018 and continues till today. It looks to build on PICASO, but take it to the next step in capturing the cyclic loading response, because that is really the main design challenge that people need to address. You can see there are 5 work packages. There's some modelling, going on, similar to work in the PISA project, but looking at more advanced techniques, some picking up on machine learning approaches. We have some calibration activities. These are lab testing, either element tests or model scale tests. We have a theoretical activity going on, developing new models and extending our theories that we have already developed for cyclic loading, which I'll touch on shortly. And then we have a major package on the field testing, really to provide the evidence of behavior under these cyclic loads. And that's quite important, because in the end, we need to find evidence of behavior in materials that are similar to those that we wish to design in and at reasonable scale. And so there was a lot of emphasis on designing and completing a really quite advanced field testing program. And then there was a package that continues, which is around exploring how you apply this new knowledge to design. So cyclic loading basics are captured in these figures in a way. The monotonic loading response is a single curve, but when the load reverses, we need to capture all sorts of behavior that comes from that load reversal. There will be some hysteresis, as the unloading path will not follow back down the loading path. There was likely to be some incremental movement, and you can see in the middle figure, as the cycling occurs, you can see the displacement is moving to the right. So we get some incremental movement per cycle. We need to capture that. There might also be some change in the stiffness. And we also need to capture the types of loadings that are being applied. For example, the middle figure shows a one-way loading going from zero to a load, whereas the figure on the right shows a loading going from if you like, the same absolute number, but different in sign, plus minus H max. And so that presents a slightly different set of behavior to that shown in the middle figure. So we need to capture all these sorts of responses. We might also want to know what is the capacity after the cycling. And we also need to remember that cyclic loading is irregular or pseudo-random. So this becomes rather complicated. And in addition, we might also want to be able to do time domain calculations if dynamics is of interest to us, where we carry out a fully integrated calculation with the turbine model. Of course, for any of these calculations, the monotonic loading is essential, and that's why there was such a focus on the PISA project first. Get the monotonic right, then you can capture the cyclic loading behavior. So here is an example of some of the cyclic loading that was carried out during the PISA project to provide some initial data for us to study. And you can see the actuator just moving away under load control, very well controlled activities. We've got lots of instrumentation. And in these tests, we were able to apply cycling over 4 or 5 days, so many tens of thousands of cycles, to try to understand the impact of the loading. So this is very important data. Because of the design setup, the loading applied can only be one way, can go from zero to a maximum load. A more complicated design can give you a two-way loading. So the typical result is shown on the left, where we have several packets of cycling. And what you can see is the hysteresis loops, but the size of these loops are a function of the absolute load of the cycling, so the magnitude of the cycling. And as you get larger loads being applied, you get more, in this case, movement to the right or ratcheting. And we need to capture that somehow in a model. The other thing you observe is the ratcheting decreases with cycle number, so it gets less as more cycles are applied. So it's a decreasing movement. The other thing you can observe is that after the cycling, you get some plastic behavior, and almost as if you move back up onto a monotonic backbone curve. And so the monotonic backbone curve becomes important. So on the right, what I have is how an existing calculation might try to capture this behavior. So you can see the calculated backbone curve or monotonic static response in red, but then you might factor it down to account for cyclic loading shown in the dark blue. And so the question really is, how does this factored response relate to the actual test? The factoring of the monotonic curve doesn't really take account of the number of cycles or the load amplitude of the cycles or anything to do if there's pseudo-random cycles. It's simply, at the most basic level, a uniform factor. So the question is really, how does this relate and how does it help us in design? In particular, it doesn't really tell us anything about stiffness or hysteresis. Here's another example result from Dunkirk. You can see, firstly, in green is a monotonic test result, starting from 0 and loading up to 200 kilonewtons. In blue is a cyclic test result, so on a different pile. And then the black line is a monotonic pushover after the blue cyclic test. And what you can observe here is that the reloading after the cycling comes back up to the original or the example monotonic response. And so the question really is whether there is any degradation at all. And the evidence that this perhaps shows is that the monotonic response actually wasn't degraded. Yes, there was some cycling and there was some movement, but on the reloading, the response regained its full, or the pile regained its full strength. So clearly it's important to capture the movements under the cycling, but also we need to recognize that under reloading, it doesn't appear as if the capacity is degraded. So a little digression. Of course, you can do lots of experiments, but you need to capture them within a theory of some form so that you can then apply the results more generally and in design. A very useful theory for capturing the behavior of foundations has been shown to be plasticity theory, in which you can capture the elastoplastic response. And in fact, you can construct theories relating to multi-surface plasticity in which you can capture hysteresis of the behavior. And so these are well-known models, have been around for many years, and have been shown to capture the sorts of phenomena we see in the pile loading tests very well. Often they are represented, sort of a multi-surface plasticity model is represented by a spring slider system, as you see on the bottom left. In order to enhance this further, to capture the ratcheting, we have introduced what we call a ratchet, this little red ratchet in the bottom, the middle left of the bottom left diagram. This ratchet allows us to add in an accumulation of the plastic strain to the model and thereby capture the ratcheting behavior. And so I won't go into the detail. There are a number of PhD theses at Oxford that you could read that give you information about this, and they're listed on the slide. But this sort of model can be applied at a macro element type level, a 1D PY Winkler type model, or even in the continuum. And it's proven to be very powerful. So the question is, how do you calibrate the ratchet? Well, it turns out, actually, we have quite a lot of data from the laboratory. And here are some data from work completed in 2010, where plotted is the normalized accumulated rotation for different loading levels. And you can see that these data are parallel to each other, but also are plotting straight lines on this log-log plot, indicating that the normalized accumulated rotation is a function of the number of cycles to a power. And so this allows us to calibrate this ratchet quite well. At least at model scale, this behavior seems very consistent. And lots of data have now been generated through various experimental campaigns to demonstrate this. Actually, the Dunkirk PISA tests also show this. Here are the data for one of the test results, also showing straight lines on a log-log plot, and the power exponent is very similar to that shown in the laboratory. So we have good confidence that this type of approach could scale across from lab to field to full scale. And actually, if you now take this approach, calibrated appropriately, and try to model the test I showed previously, one of the PISA test results from Cowden on the left, on the right, we have the calculation using this advanced plasticity model, which captures the behavior very well, which means, of course, provides a lot more information to the designer and can be much more useful in design, particularly if you're interested in time domain calculations, where you need to capture the changing stiffness with time. It also allows you to calculate the response for pseudo-random loading behavior, loading inputs. So it can be used for real world loading. So in order to develop this further, more real world evidence is needed. And so we embarked on a series of very ambitious field testing programs at 2 test sites. One was at Cowden, the same broad area as where the PISA tests were completed. And the second was at Cuxhaven in northern Germany. You can see they're roughly at the same latitude, but on opposite sides of the North Sea. The reason these types of sites are useful is because the geology of the material is very similar to that in the North Sea. And so we can find representative field testing sites onshore rather than offshore, where the testing is much more expensive. The Cowden site is a stiff clay site, the Cuxhaven site, a dense sand site. So these capture the types of materials that are most relevant to much of the design in the North Sea. The images shown are Google Maps images, so you can see the scale of what we're talking about, pretty significant. Here is the testing site at Cowden. It's a very major onshore construction activity. You can see the size of that crane. Over here, these are shipping containers. That just gives you a sense of the scale. We tested 8 1.2 meter diameter piles and 3 2.5 meter diameter piles, but also we had to install a number of reaction piles. So you can see these are the larger diameter piles, including the reaction piles. These are the smaller diameter piles. We targeted one fixed ratio of length to diameter and one fixed ratio of loading height to diameter. In the PISA testing, we actually varied those parameters quite a lot. So we didn't feel we needed to do that for these tests. The pile tests are very involved. Here is an example setup for one of the loading tests on a small diameter pile. You can see we have shipping containers either side of the pile. These are so that we can load the actuators up and apply them to the different piles. We have a reaction pile on the left and the right. The test pile is here. The actuation systems run across here. Lots of instrumentation on the pile, fiber optic strain gauges, load cells, displacement sensors, so on and so forth. Computer controlled actuators allow us to apply any loading to the pile, all load controlled. One-way cycling, two-way cycling, pseudo-random loading, whatever we want. And then at the end of the test, because these reaction piles are much larger, we can pull the pile over to fail it. That's very important. We want to see what is the capacity following the test. You can see lots of shading to make sure that the instrumentation not affected by the sunlight or rain even. Here's an example test ongoing, a two-way cycling test. You can see all the cables for all the instrumentation. You can collect a lot of information from a single test. It takes about a week to prepare the test, to construct the test, probably 2 or 3 days to do the test, and probably another week to deconstruct the test. And that's with a big team of people working around the clock to try and get this done. The sorts of loadings applied, Well, we had two two different types of testing, if you like, sort of calibration tests where we apply sort of more standard loadings. So, for example, a monotonic test where we just pull the pile over to get a reference. We also carried out some rate effect tests, looking at how the load varies under different loading rates. And then we also carried out a range of constant amplitude uniform cyclic loading. And the reason for this is that these are tests that could be most easily modeled by modelers. It's probably easier to model a uniform amplitude loading test than something more complex. And so we targeted one-way loading, 1.5-way loading, and two-way loading. We also carried out what we call validation tests, really the proof of concept. And these are random amplitude loading tests, which try to capture the types of loading that offshore wind turbines actually experience. And we did quite a lot of work to get representative load paths for these tests. The testing goes for quite a long time, probably about 24 hours of actual cycling, and then followed by a monotonic loading test to determine the final capacity. Just to show one part of the testing, but this is clearly at the end of the test where we're applying a very large amplitude displacement and load to the pile. Clearly, big gaps forming. We've got pumping of the water in the gap, and this is well past perhaps the serviceability of the pile if a structure was on top of this. But even at these displacements, the load capacity was still very significant. We could still mobilize loads consistent with the monotonic capacity. And you can see obviously the transducer here significantly affected by the water being pumped up onto it. It stopped working, I should say. So here are some examples of the loading behavior. The data is still confidential, and we're still analyzing and processing quite a lot of the information. But this gives a flavor of the types of response you see at low amplitude, fairly tight loops, probably not much displacement. There's 24 hours of cycling here, so perhaps not much movement. As the amplitude gets a bit larger, the top right, the hysteresis loops are a bit wider and perhaps a bit more displacement. And then for the high amplitude loading, you can see it only lasted for 10 minutes, but that's because we were getting quite a bit more movement, much wider, larger hysteresis loops and more movement per cycle. All of this behavior, very consistent test to test, and also very consistent with work observed in the laboratory. And we can see quite clearly that perhaps the ratcheting a function of the load level. And with this data, we can also track the stiffness and its evolution through the different loadings. Even more complex, we carried out multi-directional load testing. And so this is an image and a diagram of the setup. This is the 2.5 meter diameter pile. The loading is applied at 10 meters height, and the reaction piles are 25 meters away from the pile. So this is a very big construction and very complicated. Also for 2-day testing, fully load controlled. So probably the most complex test I would think of a pile of this scale ever completed. So on the left, I show the load paths applied in the X and Y direction. These are representative of typical loadings you might get on an offshore wind turbine. So it is representative. You can see the large storm event here, so that we're really applying very big loads to the pile to see if it can sustain it. You can also see all the instrumentation trying to measure the motion in 6 degrees of freedom. Is a complex process. Requires quite a lot of processing post the test. We had a lot of redundancy of measurement to ensure that we could capture everything. So very exciting testing and very interesting results that come from it. And then we repeated it all at Cuxhaven. So what I've shown so far is the testing at Cowden. We did it all again at Cuxhaven last year. The testing took about 12 months from start of installation to completion of the testing. This was at a quarry site. We had to excavate down to the water table so that we're testing in fully saturated material. You can see the scale of the site. Here's a pretty significant crane. Here's another image of the site. Of course, you can excavate to the water table, but over time the water table can rise. And that's what we observed, that it rose a little bit, which was very useful for the testing because it really did ensure that all of the testing was underwater. And so we were able to capture, even for piles of this scale, partially drained behaviour, where rate can play a very significant part in the load displacement response of the pile. And here is just an image of a fast rate being applied at the end of the test. And so we did, at the end of a number of the tests, we applied loads at very different loading rates to get a sense of the effective rate in this saturated dense sand at Cuxhaven. So I'll conclude with a few final remarks and really picking up from where Avi started, which was the offshore wind industry had some significant challenges about 15 years ago in design of offshore wind turbine monopiles. The PICASO project has solved at least one of those challenges, and we now design piles in a very optimized process that makes the best use of the latest computational tools and ensures that the pile design is well optimized for the loads that are likely to be seen. But as you design the piles more optimally, you need to be more concerned with the cycling that occurs. And in particular, as cycling becomes a more dominant loading because of the increase of size of the turbine and the greater impact of the wind loading relative to the wave loading, then of course you need to be much more conscious of how you're addressing the response of the pile to the cycling. So the PICASO project has been focusing on this, and we have developed these new advanced plasticity theories that allow us to compute displacements under the various loadings. We can account for rate effects, and we also can account for the fact that the monotonic behavior post the cycling doesn't appear to be degraded. And we've been able to show this works for the test piles that we've been studying. So I'll finish there and we'll take some questions. But before I finish, I will just mention the special mention for the field testing team, because very significant commitment of all of these people spending a lot of time on site over the course of 12 months. Some were involved also at Cowden and some at Cuxhaven. But it's a very challenging activity because a lot of pressure all the time when the test is ongoing, making sure we've got the measurements, making sure the testing system doesn't fail. And ultimately, it's because of great people working on site that you get great test results, which I think the PICASO project has produced. Okay, I think we will finish it there. Thank you very much for joining us. And I'll just share one last time. I'll just note the masterclass one last time. So if you're able to join and you wish to join, please scan the QR code and see you at the masterclass. Thank you very much. And I hope you all have a good afternoon.
Cheers.